For this lesson, we're going to be looking at the topic of optimization problems. Now, the idea of optimization, when we talk about optimization, what we're saying is we're trying to come up with the best possible outcome subject to a set of conditions or a set of restrictions. So when we talk about differential calculus, when we talk about the calculus of taking the derivative, this is a really large part of actually making practical use of differential calculus. So what we do is we're generally looking for a maximum or a minimum value, which we've also talked about as an extreme value, or in general the plural is just called extrema. Okay, that means any maximum or any minimum value. Sometimes the best outcome will be a maximum, but there are other situations where the best possible outcome might be a minimum. To illustrate this, we're actually going to take a look at a problem that's probably familiar to you, which is the idea of creating a box, and in particular it's an open top box. So what we do is we start off with a piece of, in this case it says a piece of sheet metal, and what we're going to do is we're actually going to cut out these corner sections, and then we will fold up these edges. So we would fold up this edge, we would fold up this edge, we would fold up this edge and this edge, and as a result we would end up forming, that's a terrible diagram. Let me take one more try at that. I'm usually not so hideous at drawing these things. Let's start with a nice rectangular front and then go from there. So that worked out a little bit better. So you can see that when I fold up those edges, so here I have the, and I'll just very quickly shade that in, I've got the base of the box here, and that would be this area, right? That's the base. And then I have the outside edges that I folded up, and I'll just show one of those. So there's one of those outside edges that I folded up, and that would be something like this part is an outside edge that's been folded up. So the dimensions on this box is it's going to have a height of x. Now when I cut an x off of here, and when I cut an x off of here, well, this original length was 60, but I've chopped off 2 x's. So this new length, which is just from here to here, that's going to be 60 minus 2x. I originally had 60 and now I've lost 2x. Vertically, I originally had 30 centimeters, but again I've chopped off a couple of x's. So I'm going to have a shortened part here vertically, and that's going to be 30 minus 2x. And then of course the actual part, the little square that I cut off each corner, results in an overall height of x. So if we think of the volume of the box as length times width times height, it doesn't actually matter which one you define. We're going to get the volume in terms of x, in terms of this little piece that we've chopped off. So the length, I'm just going to choose that to be the longest side there. So 60 minus 2x. I say longest side, I mean by appearance. It's the one with the biggest number in it. And then width is going to be 30 minus 2x. And then the height itself is just going to be x. So that's going to be the volume. Now, at this point, we're actually going to be interested in taking the derivative. So we're going to want to find v prime of x and y. Actually, before I even attempt to take that derivative, I want to answer the question, well, why are we trying to find v prime of x? We are trying to find the dimensions that will maximize volume. So if this is the volume as a function of x, then v prime of x would be the instantaneous rate of change of volume with respect to x. And so we're looking for that volume is going to increase, 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 and eventually it will reach some maximum value, and we want to find that value. And of course, if we were looking at the graph, that is also the slope of the tangent line. So however you want to think about this is fine. We're going to have to find this first derivative, and we're going to have to set it to 0. Now there's a couple of ways you could do this. You could, for example, expand all of this out and turn it into a simple polynomial. You could Well, what's the problem with the way it is right now is we actually have three factors multiplied together, which means essentially we have three distinct functions. So let's go ahead. I'm going to grab a new sheet. I don't want any single page getting too long here. So I think what I'll do is I'm going to copy what I've got here. So let's copy that. Let's move to a new page. Let's paste that there. Okay. And so now, what are some options? So one, I could just expand everything. And that's doable. This is going to turn into a cubic. It's not terrible. A second that I could do is I could expand one bracket, and that would give me v of x. If I expanded one, and for example, if I was going to expand one, I might do this pair. So maybe I'll say one bracket pair. If I did that, then if I could combine these ones together, and that would give me 30x minus 2x squared. And that's not terrible to do. That was quite easy. And then we would end up with v of x would be the product of two distinct brackets. And then I could use the product rule on that. Or a third option is we could just use the product rule on v of x, and I'm just going to treat that as if it was f times g times h, where f and g and h are the three different functions. Now I only mention this here because I know I've talked about it in a previous lesson, and I just want to explain, well, how would I do it? What if expanding it wasn't an option? What if simplifying it wasn't an option? What if I had to work with these three functions? So I'm just going to highlight that for a moment. And the way that you would do that is we actually group one of the pairs. So instead of treating this as f times g times h, I actually treat this as f times g times h. So what I'm going to do is v prime of x is the derivative of the first, which is f prime, multiplied by the second, which is just gh, plus the first, which is f, multiplied by the derivative of the second. So that is going to be gh, and I'm just going to put the little prime outside of that bracket to say I have to take the derivative of this whole thing. A better notation for this would be to use Leibniz notation. So that would be df by dx multiplied by gh plus f multiplied by d of gh by dx. So I take the derivative of f and leave the other two alone. Then I leave f alone and I multiply that by the derivative of the other two. Now the key here is, well, what is whether you're looking at it from here or here, what is the derivative of gh? Well, that's going to be the derivative of the first times the second plus the first times the derivative of the second. Oh, I wrote squared. I meant derivative. So that meant prime. And so if I put those together, I end up with f prime, which was right here, multiplied by g multiplied by h, plus f, but in this bracket I have to put g prime h plus gh prime. And then if I expand out that bracket, f prime gh plus f times g prime h plus fg times h prime. And the pattern here actually ends up being quite simple. We end up with the derivative of the first times the second times the third, plus the first times the derivative of the second times the third, plus the first times the second times the derivative of the third. So notice that I multiply out my product 3 times, but I take the derivative of the first function in the first term, the second function in the second term, the third function in the third term. How you approach this is entirely up to you, how you use these tools. I just want you to be aware that you do have options. So now let's actually get to solving the problem. So once again, working from there. So v prime of x is equal to, and I'm just going to use that product rule that we just developed. So it's going to be the derivative of the first, which is the derivative of this is just negative 2 multiplied by 30 minus 2x times x, plus the first, which is 60 minus 2x, multiplied by the derivative of the second, which is negative 2, times x, which is the third, plus 60 minus 2x times 30 minus 2x multiplied by the derivative, which is 1. So I'm just going to make a note here to say here was a derivative, here was a derivative, and here was a derivative. Now I've taken the derivative of the whole thing. So I'm going to go ahead and expand these and simplify them. So I end up with negative 2 times 30 is negative 60x. Negative 2 times negative 2x is positive 4x, so that's plus 4x squared. This one's going to be negative 2x minus 120x, negative 2 positive 4x squared. This one's going to be 1800. And this one's going, oh, this is actually a full expansion. So first outer is going to be minus 120x. Inner is going to be minus 60x. And last is going to be plus 4x squared. I'm going to gather like terms. 4x squared, 4x squared, 4x squared. I end up with 12x squared. And then I have, let's see, for my x's, I have minus 180x, minus 300x, minus 360x. And finally, I have, let's see, for my constants, 1800. So plus 1800. So from there, I'm going to set that equal to 0. So I set v prime x equal to 0. And I end up with 0 equals 12x squared minus 360x plus 1800. I notice right away I can actually divide all of these by 12. And so I'm just going to divide both sides by 12. This is the same thing as if I factored out a 12. And so of course I stay at 0 there and I end up with x squared. And then divide that by 12 becomes minus 30x. And divide that one by 12 is 150. So that's a pretty reasonable looking quadratic that I've got here. Unfortunately, it's not going to be factorable using integer values or rational values. So we're going to end up having to use the quadratic formula for this. Now b squared minus 4ac is going to be positive. It's going to actually have two solutions. B squared is negative 30 squared, which is 900, minus 4ac is minus 600, so it's positive. And so I use the quadratic formula to solve for x. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And I've already got an answer ready for this one just for the sake of time. I end up with x is approximately equal to 23.660, or x is approximately equal to 6.340. So you take a look at this and these seem like valid answers. They're both positive. Okay, so is there a problem? And the thing we have to check now, let's see, again, I think I'm going to open up a new page for this one so I can continue from here. So I'll copy that, go to a new page. Okay, so now we have to concern ourselves with the domain. And what do I mean by the domain? I mean that all dimensions must be positive. It's not enough for x to be positive. Remember, we've got this overall shape, which is an x here, a 30 minus 2x here, and a 60 minus 2x there. All of these have to be positive. So yes, the x is positive for both of these, but if we try out some of these values, so for example, well, we could do this two different ways. We could go ahead and sub these values in, or we could just take a look at our x must be greater than 0. Okay, so that's already satisfied because both of these x's are greater than 0. 60 minus 2x must be greater than 0, which means that 60 must be greater than 2x, which we could flip around. That's to say 2x must be less than 60, or x must be less than 30. I take a look at those. Yeah, they're both x less than 30. And 30 minus 2x must be greater than 0, which means that 30 must be greater than 2x, or 2x must be less than 30, x must be less than 15. Oh, hold on a second. X less than 15 means that we are going to reject one of our solutions. We're going to reject x is approximately equal to 23.660. And so by rejecting that, we actually only have one value left. And so as a result, therefore, x must be equal to, and what was our answer? 6.340. And I believe the question actually wanted to know what were the dimensions of the box. And so for that, now I have to sub in my values. So for example, 60 minus 2 times 6.340, that dimension is going to give me 47.32 approximately. And 30 minus 2 times 6.340 is going to give me approximately 17.32. And so now we finish off with our concluding statement. Therefore, the dimensions to optimize or to maximize area, it's not area, it's volume, are 6.3 centimeters by 17.3 centimeters by 47.3 centimeters. And I don't believe the question specified number of decimal places, and so that's why I've just gone ahead and I've rounded everything to a consistent level to one decimal place. In that case, just in case any rounding that I did before is not going to impact these answers. Whether you keep all the digits or you do a little bit of rounding, your answers should match those. Now, that was single question, despite my little bit of I went off on a tangent talking about how to take the derivative using a product of three functions. Now, to be honest with you, I just want to mention it was actually easier to have expanded that and done the derivative that way, and I won't argue with that. I just wanted you to see a different way of doing it. Now, in general, if we're solving an optimization problem, the first thing is you need to read the problem. Make sure you understand what it is that's being asked for. Make sure you understand the difference between the original function and the derivative of the function, what the derivative is going to tell you. If you can, you're going to draw a diagram. At some point in time, you're probably going to have to think about the domain of the function. You might be able to come up with something before you start, or you might have to look at it afterwards. Don't forget to look at any endpoints, if they exist, to decide whether or not you have maximum or minimum values, and then go ahead and answer the original problem. And that's it. There's a bunch of problems here. These are all application problems, so they're generally word problems. They're going to take you a bit of time to get through, and Just make sure you're really careful about these. This is getting into algebraically. These can be quite involved, and a small mistake can really derail you going forward.